All right, so let's start 5.1. 5.1 is the beginning of chapter 5. Chapter 5 is going to be a lot like what we did in chapter 4. We're just dealing with a different function. So remember, chapter 4 was all about rationals, okay? Chapter 5 is all about radicals. And the layout of this chapter is just like chapter 4. You learn how to do some simplifying first. That's what 5.1 is all about with radicals. Just like in 4.1, you learn how to simplify rationals, and this is going to be extremely, extremely important moving through everything from the rest of this chapter because you are going to have to be able to simplify radicals. They do not want decimal answers. So you need to simplify radicals. And then you'll learn how to add, subtract, multiply, divide, and then some other little special things about radicals and stuff like that too. So that's what chapter 5 is about. This will end module 3 for us. And so let's go ahead and get started. So a couple things first. I want to talk to you about the calculator. So the calculator, I want to show you where your radicals are at. So if you hit second and x squared, right there's our radical. See how it pops up? But we're going to be dealing with not just square roots, but we're also going to be dealing with cube roots and fourth roots and fifth roots and sixth roots. Oh my. So I want to show you how you can get those. So if you click on math and right down here, number 4, there's a cube root, but I want to talk about number 5 because I like number 5 better than just choosing number 4. Because number 5 will let you do any radical that you want. So you click on number 5, see right up here it's blinking. Right in here, you just put the number of your root. So if it's a cube root, you can put 3 there. Or if it's a fourth root, you put 4 there. Fifth root, you put 5. Sixth root, you put 6. And then in here, you put your number. So that's what that math number 5 is all about. Allows you to do any root that you want. Okay? So I like number 5. And then I also use the second and the x squared on the outside to help me with square roots. Okay? So those are going to be some keys that you use a lot in here. And then also that you're going to want to have handy for you. This chart that I've given you, these are numbers that we care about the most. So PS stands for perfect squares. PC stands for perfect cubes, perfect fourths, perfect fifths, perfect sixths. So what a perfect square is, PS, is these numbers. A perfect square is just a number that is times itself. Or in other words, a number squared. Okay? So it's just a number times itself. So to get 4, well, that's just 2 times 2, or 2 squared. Hence, perfect square. 9 is 3 times 3, or 3 squared. 16 is 4 times 4, 4 squared. And so on and so forth. So these are your first 15 perfect squares. Right here, this is perfect cube, perfect fourth, perfect fifth, perfect sixth. So perfect cube, these are numbers times itself 3 times. So perfect cube is just a number cubed. Like 8 here is just a 2 times 2 times 2. That's what a perfect cube looks like. 27 is 3 times 3 times 3. And so on and so forth. Notice I stop it after 6 cubed because these things get large and they get large quick. You can see that with all the other ones. So perfect fourth is just a number times itself 4 times, or the number to the 4th power. So 16 is 2 times 2 times 2 times 2. Okay? 81 is 3 times 3 times 3 times 3. So if you ever forget this list, you can always make them, because just remember, a perfect cube is just a number times itself. A perfect cube is a number times itself 3 times, and so on and so forth. This is going to be super important for us when we want to reduce. Okay? So let's talk about simplifying radicals. So again, this is uber important for everything that is to come. All right? You need to know how to simplify for the rest of chapter 5. All right. So moving on over here. I've got 7 examples here. And right now, I'm going to get you the basics of radicals. Okay? So in here, we're going to be talking about the basic of radicals. So I'm going to start you off pretty easy, and most of what we're going to be dealing with are like perfect squares and things like that. So when we look at this, starting with right here, the square root of 25, well, if you go back to our list, you can see 25 is a perfect square. And I know that I want to look at those because this is a square root. When you're dealing with square roots, you'll work with perfect squares. When you're dealing with cube roots, you'll work with perfect cubes. Okay? If you have a fourth root, you'll be working with perfect fourths, and so on and so forth. So you saw that this number was on our list of perfect squares. That's because 25 is 5 squared. Okay? And so you're taking the square root of an item squared, and hopefully you kind of remember some things and know that whenever your root matches the power, all they do is cancel each other out, leaving you with 5. So the answer to the square root of 25 is 5, because what's going on behind the scenes is that this is a perfect square of 5 squared, and the root is canceling out the power because they are the same. Okay? So whenever the root is the same as the power, they cancel each other out. Okay? And over here, I've got some properties. I'm going to show you a lot of properties. But what we're talking about is what we're dealing with right here. If you look at this guy that's right there, that's what we just talked about. Whenever your root is the same as the power, they just cancel each other out. And the same thing if you have a cube root, and the power on whatever you're dealing with is the same. They just cancel each other out. A cube root takes care of a cube. This property also works if you have a square root and you're going to square it. Because again, these are opposites of each other. The opposite of a square root is a square, so they just cancel each other out, leaving you with x. And the same thing can happen in the case of the cubic. I could have a cube root of x, raise it to the third power, and they just cancel each other out because they're the same. The root power is the same as the power. Okay? So let's go and let's look at this next piece. And also, you could go into the calculator and run this. If I hit second y squared or x squared, 25, hit enter. Oops, too much. Let's actually make it a 25. Delete. See? 5. That's because it's a perfect square. We like perfect squares. Perfect squares make our lives easy. So now when you look at this next one, notice you have a radical and you have a fraction under the radical. Okay? So if you just saw, we're looking a minute ago, you saw that we had a piece like that over here. I have a radical and a fraction under it. Whenever I have a radical and a fraction under it, cool thing is I can actually take it apart. I can separate them. I can have a radical on top and I can have the radical on bottom. And the same thing works if it was a cubic, a fourth root, you can just separate them out. So whenever you have a fraction under a radical, whatever the radical is, separate them. And that's what's cool about this is because when I separate them, notice that these numbers are perfect squares. They are all on my list. See, there's the 4, there's the 81. And that means that these should come out nice and neat. So if you go to your calculator and run the square root of 4, you get 2. You go to your calculator, run the square root of 81, you get 9. Okay? And that's the answer. Again, just to show you, go to your calculator, second x squared, 4, 2. Second x squared, 9, 3. Sorry, square root of 81. Square root of 81 is 9. And there you go. So 2 over 9. All right. So now I want to talk about these two right here. What do we do with negatives under a radical? Well, let's go over here and look at some of our pieces of information. So we've talked about that guy. Let's talk about these two right here. This is what we're dealing with. So whenever you have a radical, or in other words, in this one, a square root of a negative number, we're going to say that it does not exist. So right now, so you know, from 5,1 all the way to 5,5, if you're going to take a square root of a negative number, that answer does not exist. Okay? But if you're going to take a cube root of a negative number, then we can deal with that because the negative under the radical will pop out front. And then you'll just be dealing with the cube root of the number. Okay? So right now, I want to kind of expand this so you know. If you have an even root of a negative number, I want you to know that anytime it's an even root, so that's like a square root, a fourth root, a sixth root, an eighth root, a 10th root, so on and so forth, anytime you have an even root, the answer will always be does not exist. Now down here, anytime you have an odd root of a negative number, that negative will pop out just like before, and you'll have an odd root of the positive number left. So, even root does not exist. Odd roots, like a cube root, a fifth root, a seventh root, a ninth root, 11th root, the negative pops out front, and you're left with the positive version of the number under the odd root. Okay? So, looking at these, this is an even root. It is a square root of a negative 4. And as we said a second ago, this does not exist for us right now. When you get to 5.6, we'll turn that on its head and we'll talk about how we can deal with an actual negative number under an even root. And again, you can actually verify this with your calculator, hitting second x squared, put in -4, and the calculator says error, non-real answer. We'll talk more about this when we hit 5.6 and what that really means. Okay? So negative numbers under even roots do not exist for us. Now this guy, well, I've got a negative number under a cube root. So all that's going to happen is we're going to take that negative, we're going to pop it out front. So that gives us 2 negatives out front. And underneath the cube root, we'll have a positive 125. Well, what happens with 2 negatives out front? They just cancel each other out. They become positive. So this is really what we're dealing with, the cube root of 125. And since this is a cube root, we're going to look at perfect cubes. And if we come over here, oh, look, there's 125. It's on my list. That means this number will come out nice and neat. So let's go to our calculator, hit math, and I'm going to go down to number 5. Yes, I know it's a cube root, so I could use 4, but I want to show you number 5 in action. So it is a cube root, and then underneath that, I got 125. Enter. So the answer is 5. Okay? So there we go. I got 3 problems left right here. I want you to go ahead and pause the video. Think about these pieces that we talked about right here, the blue dots, the green dot, and the red dot, and see if you can get through these last 3. And go. Okay. So these last 3 are a lot like what we talked about right here in the first piece. This is a square root. The power is a square. Because this is a square root and that's a power of 2, they just cancel each other out. So what am I left with? -12. This is just like what was going on right there. This square root cancels out that power of 2. And there you go. Okay? And now I know some of you are like, Mr. Armstrong, that's a negative number under the even radical. That is true, but you can't worry about the negative number because you got this power of 2 and this radical right there. They really do just cancel each other out. So you don't really worry about that. Okay? So over here, again, you got the same situation. You've got a cube root and a cube as a power. So in the end, they can just cancel each other out. You're left with 6. And last but not least, the same thing, even though I know you got a variable here, but it's just about the cube root taking out the power. And you're left with x plus 12. See? Not too bad, right? Getting used to some things. Now, there is one extra property over here I didn't talk about, and that's the last one. So in this one, when your roots are the same, all that's going to happen when you're multiplying the same roots, the number pops out. And by the same, I'll show you what I mean by here. Like if I'm taking the square root of 4 times the square root of 4, you see how everything is the same. Then that means the number 4 will pop out. That's what that final property right there is about. When you're multiplying the same radicals, the number pops out. Again, just another example, square root of 7 times the square root of 7. These two radicals are the same. The number pops out. All right. So let's do some more simplifying. Now I'm going to ramp it up a little bit. So if you look at these and you go back and look at our list, none of these numbers are on the list. Okay? So I'm going to show you 2 ways that we need to simplify these because they can simplify. I'm going to give you 2 methods. All right? I don't care which method you pick. I just need you to choose one of them. All right? So the first thing that we're going to deal with is the square root of 8. Okay. So with the square root of 8, my first method that I'm going to show you, method number 1, is what I call good child, bad child. Okay? So what we're going to do with this square root of 8 is we're going to use a property. And this is the last property I'm going to show you. And this property says that if you have 2 numbers under a radical that are being multiplied, we can separate them. That's just like what we talked about right here with when I have division under a radical. If I have division under a radical, I can separate them. I can do the same thing with multiplication. I've got 2 numbers under a radical that are being multiplied. I can separate them out. Okay? Oops, too far. So what times what gives me 8? Well, 4 and 2. Yes, I know 8 and 1 works, but we want to work with perfect squares. Okay, and I'll talk more about that here in a second. So 4 times 2 gives me 8. Well, I have 2 numbers being multiplied under a radical. I can separate them. 4 and 2. This is what I call the good child. This is what I call the bad child. The reason why this is the good child is because 4 is on my perfect squares list. See, it's right there, 4. That's why it's a good child. It is perfect. Okay? And as a good child, the square root of 4 we know to be the value 2. So all good children get to go outside the house and play. So the square root of 4 becomes 2. See, it's outside. No more radical. It's outside the house. Now, this is the bad child because 2 is not on my list of perfect squares. And since you're a bad child, do you get to go outside and play? Heck no. You be like, get back in your cage before I get the hose again. Bad child always stays inside. Perfect squares, you take the square root, they go outside. Bad child stays inside. And that's what I call good child, bad child. So we now know that the square root of 8 breaks down into 2 square roots of 2. Okay? Now, on those other 4 problems that I have on that other page, I will be doing good child, bad child, and I will do the second method I'm about to show you, which that second method we have is called the tree diagram. Okay, I will show you on these 5 examples both methods. After these 5, I will use nothing but the good child, bad child. That's how I was taught. This is the easiest method for me, and plus it takes the less work. But some people like the tree diagram a lot, so I like to show it as well. Okay, so we're going to take 8, and I call this a tree diagram because you're going to break it up into its prime factorizations. So we're going to make a prime factor tree. So what times what gives me 8? Well, that's 4 times 2. 2 is prime. Remember, prime numbers are any number that is just 1 times itself. So 2 is prime because the only way to make 2 is 1 times 2. 7 is prime because the only way to make 7 is 1 times 7. 11 is prime. The only way to make 11 is 1 times 11. 4 is not prime. So what is 4 made up of? 2 and 2. Now we have the prime factorization of 8. All we're going to do now, because we're dealing with a square root, square roots care about pairs of numbers. Okay? So in here, I'm going to circle pairs of numbers I have. And I have 1 pair of 2s. Okay? There are no other pairs. Once you're paired up, you can't use them again. So pairs are like my good children. They get to go outside. And so I'm going to take my pair and write out the number that represents the pair. So I had a pair of 2s, so I write a 2 in front. If you did not get paired, you go back inside the house. So this guy did not get paired, it went back in. Again, so any pairs I circle, the number of the pairs goes out front. Anybody not circled goes back indoors. And see, same answer, 2 squared to 2. So again, when you're dealing with square roots, you're going to look for pairs. If it's a cube root, you'll look for triples. If it is a fourth root, you'll look for groups of 4, and so on and so forth. Okay, so those are the 2 methods. I don't care which one you use as long as you can simplify the radical, because that's the important part. All right, so let's talk 50, and I'm going to do good child, bad child first, and then we'll do the tree diagram. So the square root of 50. So we're going to go back to our list, and it's a square root, so I'm dealing with perfect squares. So I want to know the biggest perfect square that's going to divide 50. Okay? That's how I do good child, bad child. So when I had that square root of 8, I only had to worry about 1 and 4. Now we know that 1 always divides everything. But when I'm looking for the good child, I'm looking for the biggest perfect square that divides the number. I call that the GPS. Okay? So when you are simplifying using good child, bad child, you're looking for the GPS, the greatest perfect square. Okay? If it's a square root. If it's a cube root, you'll be looking for the greatest perfect cube, or the GPC, and so on and so forth. So when I had 8, I only worried about 1 and 4, because 9 will never divide into 8. Okay? So if I tested 1, you would have saw that it worked. But again, if I tested 4, 8 can be divided by 4, so this was the biggest perfect square that divided 8. Okay? So let's talk about 50 now. So I'm going to test all the numbers all the way down to 49, because I know 50 is not divisible by 64. It can't. 64 is too big. Okay? So I'm going to go to my calculator, and I'm going to see in here what is the biggest number that divides in my perfect squares. Okay? So 50 divided by 1. That works. So far 1 is the biggest. Well, let's try the next guy. 50 divided by 4. Nope, it's a decimal. Doesn't work. 50 divided by 9. Nope, decimal. 50 divided by 16. Nope, decimal. 50 divided by 25. Hey, that worked. So this is now my biggest perfect square so far, 25. 50 divided by 36. Nope. And 50 divided by 49, we know that's not going to work. So what was the biggest perfect square that divided it? What's my GPS? 25. So we go back to our problem. And I've got the square root of 25. And then I've got the square root. Well, what times 25 gives me 50? And if you look right there, that's the 2. So now I know my good child and my bad. Good child gets to go out and play. What's the square root of 25? And that's 5. Bad child, get back in the house. You can't go outside and play. And there's how the square root of 50 reduces according to good child, bad child. If we did the tree diagram, so what times what gives me 50? Well, 25 and 2. You could have also used 10 and 5. That would have been fine. Okay, you just got to, break it down into its primes. So 2 is prime, 25 is not. 25 is made up of 5 times 5, and the 5s are prime. So 50 is 2 times 5 times 5. Because this is a square root, we're circling pairs. So I've got a pair of 5s. No one pairs up with the 2. So my pair of 5s, they go outside and become 5. My 2 goes back inside. See? Matches. All right, let's do 98. So 98, good child, bad child first. Okay, so if I go up to my list and I look in here, 98, so that means I'm going to test all the way up to 81. So I want to know in here, what's the biggest perfect square that's going to divide 98? I already know 1's going to work, but let's just start with the next one. 98 divided by 4. Nope. 98 divided by 9. Nope. 98 divided by 16. Nope. 98 divided by 25. I'm only testing perfect squares. 98 divided by 36. Nope. 98 divided by 49. Hey, there it is. There's 1. So 49 is our biggest perfect square so far. And then 98 divided by 64, because I want to make sure that that's the biggest. And then 98 divided by 81, which we know ain't going to work. So our biggest perfect square for 98 was 49. Okay? So we go back to our number. And so we've got 49 as our perfect child. What times 49 gave me 98? And that was 2. Perfect child gets to go out and play. So that's 7. Bad child, get back in your cage. Stays at home. And that's how the square root of 98 breaks down. If you did the factor tree, it would look like this. Well, 49 and 2. 2 is prime, 49 is not. 49 is 7 and 7. Those are prime. So 98 is 2 times 7 times 7. It's a square root, so we're circling pairs. Circle. So the 7 goes outside because that's my pair. And then the 2 goes back inside. Okay? Let's try this guy real quick, and then I want you to try the last one on your own. So you got a negative under a radical. So taking what we just knew before, we're going to pull that negative out. And what I'm dealing with is the cube root of 16. Since this is a cube root, I'm worried about perfect cubes. So I'm in this column now. And since it's 16, I only need to try the first 2 numbers. Well, you know that one will always work, just so you know. So really, you can just start at the next level. So all I want to know is, does 8 divide 16? And yes, it does. Okay? 16 divided by 8. See, it divides it. So when we go back to our problem, this breaks down into with a negative in front. Almost forgot that. And you have the cube root of 8 and the cube root of 2. Just so you know, the bad child it seems that it's always the square root of 2. That's not true. Just on these examples that I've chosen, it's always been the square root of 2 or the cube root of 2 that follows. So what's the cube root of 8? That's the good perfect child because it's a perfect cube. That gives us a negative 2. Cube root of 2 stays because it's the bad child. You don't get to go out and play because you're mean. All right. If we did the tree diagram to this, well, we've got 16. What times what gives me 16? Well, that's 8 and 2. 2's prime, 8 is not. 8 is not. What times what gives me 8? 4 and 2. 2 is prime, 4 is not. What times what gives me 4? 2 and 2. Primes. So 16 is 2 times 2 times 2 times 2. And because this is a cube root, we are circling triples this time. So there's a triple. So this triple goes outside, which is why we have the 2 outside, because that's the number of the triple. This 2, because it didn't have anybody, goes back inside. And there you go. All right. So pause the video. Give this last one a shot. Okay, let's zoom in on this so that way we can come down here and work on it. So again, we're dealing with cube roots. Okay, that negative will pop out. So we have a negative. Well, let's do it over here to the side. So we have a negative cube root of 54. So if we go back to our list, since it's 54, I'm going to be worried about which number up here, 1, 8, 27, is the biggest that divides it. Again, I don't go to 64 because that's too big. 64 is bigger than 54. Okay? So scroll back down. Oops. Scroll back down. Expand my page a little bit. Okay. So if I go in here, 54 divided by 8, did that work? Nope. 54 divided by 27, did that work? Yep. So we know that this guy breaks up into the cube root of 27 and the cube root of 2. What's the cube root of 27? That is 3. Cube root of 2 stays. And there you go. Over here, if we did the tree diagram, 54, it breaks down into 27 and 2. 2 is prime, 27 is not. 27 is 9 and 3. 3 is prime, 9 is not. 3 and 3. So 27 or 54 is 2 times 3 times 3 times 3. Again, it's a cube root, so you circle triples. Now you see why this 3 is out here, because I have triple 3s. So the 3 pops out, and that 2 goes back underneath. And that's how we simplify radicals. Again, from here on out, I'm only going to do good child and bad child. Okay? All right. So this is as tough as what it's going to get. We've got to talk about variables and how we deal with those. And again, I'm going to show you 2 methods to deal with variables. All right. So as we look at this problem, here's how I want you to think about it. Okay. I want you to think about this as 3 separate pieces, and I want you to separate it out. Because remember, anything that's being multiplied under the radical, we can separate them. So this is like we're dealing with 3 separate problems. Square root of 4, square root of x cubed, square root of y to the 5th. Okay? So square root of 4, you actually already know. That's a perfect square. That is 2. Now these other 2, this is what I want to talk to you about. I'm going to show you 2 methods. Okay? So method number 1, I call it the circle method. And it's just like the tree diagram method, although we're not worried about prime factorizations. we're going to be worried about groups that are escaping. Because when I think about these, x to the third, and the square root of y to the fifth, I think about this like a jailbreak. Your variables are trying to break out of jail. The only way that variables can break out of jail here is if they are in groups of 2, hence because we are a square root. So what does x cubed really look like? Well, it looks like x times x times x. So just like before when we did the tree diagram, we're worried about pairs. How many pairs of x's can escape the jail? 1 pair. This guy can't escape. He's going to go back inside the jail. So when we write this out, how many groups of x's escaped? There was 1 group of x's that escaped. This guy got left behind. That's how the square root of x cubed breaks down. Using that same logic, y to the fifth looks like y times y times y times y times y. Again, it's a square root, so only pairs can break out of jail. So, how many pairs of y's broke out? There were 2. Notice that the number of pairs that breaks out, they come up in as a power. 1 pair broke out, so that's a power of 1. 2 pairs broke out, so that's a power of 2. This y did not break out, so you're back underneath the jail. And that's how it breaks down. So now we know that this is x square root of x. This is y squared square root of y. I'll talk about how to finish this out in just a second because I want to talk about the second method to this. The second method I call is dividing. The reason why I call this dividing, this method is good. Most of our, well, actually pretty much almost all of our problems, you can do this where you write out all the variables and do your circling, okay? But let's say I gave you something like this. X to the 103rd. I don't see you guys writing out 103 x's and going through and doing all the circling. That's just crazy. Okay. Also, not very time effective. So this is what I call division. Okay. So we're going to take that power of 103 and we're going to divide it by what we would have circled. Because this is a square root, we're circling pairs. So I'm going to divide it by 2. Okay. Well, if you go to your calculator and divide 103 by 2, you get 51 point some sort of decimal, blah, 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 blah. I don't really care about the decimal, but I'll talk about what's going on here in a second. Okay, so when you divide that, you get 51 point some decimal, and that's actually just 0.5, but I don't really care about the decimal. So what this number tells you is that this first number, that's how many pairs of x's are escaping. That whole number there is how many pairs of x's you would have circled. So if you wrote out 103 x's, you would have had 51 circles. Okay? The decimal, what that signifies is if there's a decimal there, that means that there are some variables left behind. So whenever you do the division and you have a decimal, that means there are variables left behind. How do I figure out how many are left behind? You're going to multiply those two numbers. And then you are going to subtract from the numerator. So 2 times 51 is 102. 103 minus 102 leaves you with 1. So that means there was 1 x that got left behind. Okay? So you can see why I wanted to talk to you about the division, because sometimes if you have crazy exponents, it's crazy to write it all out and do your circling. The division one is going to help you get through that. So if I look at these up here doing the division, so for the x's, I had 3 and I was circling pairs. I go to my calculator, I get 1 point blah, 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 which is 5, but it doesn't really matter. So I now know that 1x escaped. Because I have a decimal, that means I have some left over. Well, 2 times 1 is 2. Minus 3 is 1. So I had one x left inside. And doing the same thing for the y's. I had 5 y's, and I'm circling pairs. If I do my division, I get 2 point blah, blah, blah. So that means 2 pairs of y's escaped. And because I have a decimal, I have some left over. So 2 times 2 is 4. Minus 5 gives us 1 y that's left over. Okay? So now, how to wrap this up? All we do is rewrite the pieces that are out front, like the 2, the x, and the y squared. We're going to write those first. So everybody that escaped gets written down. And then you'll put your radical and tell me everybody that's left inside. So I've got an x left inside and a y left inside. And there you go. That's as hard as simplifying is going to get. Okay? So let's take a look at this. Actually, go ahead and pause the video. Try these other 3. And go. Okay. So up here, I'm just going to break this apart. So we got square root of 81, square root of m squared, square root of n to the 3rd, square root of o to the 7th. Okay? Taking this piece by piece, well, this is a perfect square, so we already know what that comes out to. That's 8. I've got a square root and a square from what we talked about earlier. They would just cancel each other out. So you don't actually have to write out the m's there. But if you did, again, it would just be m times m. And you're circling pairs because it's a square root. So you can see that one pair of m's escapes. Okay? Over here, well, we've got n times n times n. We're circling pairs because it's a square root. So one pair of n's escapes, and this other n that's right there gets back inside. Now over here, I don't really want to write out 7 o's, so I'm going to take 7 divided by 2 because we're circling pairs. That gives us 3 point blah, blah, blah. So we now know that 3 pairs of o's escaped. We have a decimal, so there are some left inside. So 2 times 3 is 6. Subtract 7 from that. You get 1 O left inside. Now that we've done all the simplifying, put everything together. So out front, I have an 8, an M, an N, and an O to the 3rd. 8, M, N, O to the 3rd. Inside my radical, I've got N and O. And there we go. Scrolling on down. So if we break this guy up, 4th root of 32, 4th root of u to the 3rd, 4th root of v to the 4th, 4th root of w to the 5th, 4th root of y to the 7th. All right, so if we look at this, if you go back to our list of perfect fourths, 32 is not on our list. But we can try and see if one of these two divides it to help us break it down, just like what we did before. So if I go to my calculator, 32 divided by 16, because we know 1 will work. Oh, it works. So this is the biggest perfect fourth that divides it. So we can do good child, bad child to this. So going back to our page. So we're going to break this up. 4th root of 16. 4th root of 2. The good child gets to go outside and play. The 4th root of 16 is 2. This is the bad child, so it stays indoors. All right. Now we look at the next one. If you look at this one, notice that it takes 4 to escape. How many do I have in here? I have 3. So this is actually good the way it is. None of these u's are escaping because, again, if you draw those out, I've got u times u times u. I got to circle 4s, pair of 4s. Or, sorry, not pair of 4s. I got to circle groups of 4. I only have 3. So, again, no one's escaping. So that u to the third stays. That's good. This one over here, oh, a 4th root and a power of 4. Well, we know those just cancel each other out. So that leaves you with v. And again, if you wrote that out, v times v times v times v, circling groups of 4. See, one group of 4 v's breaks out. W to the 5th, well, again, w times w times w times w times w. We're circling groups of 4s. So there is one group of w's that escapes and one guy that gets left behind in jail. Okay? This last one, I'll do division on. So I'll take 7 divided by 4 because I don't really want to write out 7 y's. So 7 divided by 4, well, that's 1 point blah, blah, blah. So I now know that there is one group of y's that escapes. Okay. So because I have a decimal, that means some are left over. So we're going to multiply. 4 times 1 is 4. And then we'll subtract that from 7. 7 minus 4 is 3. So I have 3 y's that did not escape. And now all we do is we just put it all together. So anybody that escaped goes in front. So 2 v w y. 2 v w y. And then we put up our jail, which is the 4th root. What do we have left inside? We have a 2. We have a u cubed. No v's. We have a w. And we have a y to the 3rd. And there it is. That's it. Last problem, and then that will end simplifying. We just got 2 other concepts to talk about here in a second. So in here, so we've got the 6th root of 128. We've got the 6th root of v to the 4th. We got a 6th root of w to the 5th. And we've got a 6th root of y to the 7th. Okay? So if you go and look at our perfect 6th, 128 is not on there. So really all I have to do is check the 64. Okay? So if I go to my calculator, 128 divided by 64. Hey, it works. So this is the perfect 6, the biggest one, that divides it. All right. So let's go back to our page. So we got to break this down. And I'm only using good child, bad child. You can always do the tree diagram. So this is the 6th root of 64 and the 6th root of 2, because 2 times 64 is 128. This is the good child and becomes the number 2. This is the bad child, so the 6th root of 2 stays. Looking at the rest of these, the next 2 are just like what we did with the u to the 3rd with the 4th root. I only have 4 v's. I need 6 to escape, so this is fine. I only have 5 w's, but I need 6 to escape, so there's nothing that's going to happen there. That has to stay the way it is. Okay? Then over here, now this one, the one time I will write out 7, 1, 2, 3, 4, 5, 6, 7. So in order to escape, I got to have groups of 6. So I have one group of 6 y's that can escape. I've got one left over. You're back in the jail. So writing down what we have, the pieces that escape are 2 and y. The pieces that are back in my jail are 2. I've got a W to or a V to the 4th. I've got a W to the 5th. And I've got a Y. And there it is. That is simplifying of radicals. So the last 2 pieces in your guys' 5.1, they're going to talk about Pythagorean theorem, and you're also going to be doing some evaluating. So these. Okay? So let's talk about Pythagorean theorem real quick, and I've got 2 examples. One of them will work together. One of them I will have you try on your own. So Pythagorean theorem states that if you have a right triangle, then the sum of the squares of the legs equals the square of the hypotenuse. Or as many of you would tell me, Mr. Armstrong, the Pythagorean theorem is a squared plus b squared equal to c squared. And I will be like, you're absolutely correct. But you got to understand that these pieces of A, B, and C represent pieces on the right triangle. A and B, they are those legs that they're talking about up here. And A and B are located right here. They are the legs. Please understand that this is always true. The legs are always connected to this symbol right there. That symbol means perpendicular, which means that that is the right angle. The legs are always attached to the right angle. That's where a lot of students will get messed up because one of you, and it never fails, will put a C value here. The C value, which is called the hypotenuse, is right here. The hypotenuse is always across from the right angle. The hypotenuse is always the longest side of the triangle. Okay? The hypotenuse is always the longest side. It should be the biggest number out of the 3. Legs are always attached to the right angle, to the 90 degrees, to the perpendicular symbol you see there. Okay? All you got to do for these, and these are going to be your word problems. My advice to you, just like in geometry, draw a picture and then plug in what you know where it goes. Okay? I can't stress this enough. Draw yourself a picture. All right? Legs are always attached to the perpendicular degree symbol, the 90 degrees. Hypotenuse is always the longest side. Let's do this. So here we go. It says, in order to clean a 25-foot high window, one of our Osceola maintenance persons, Young Sue, needs to put a ladder 10 feet away from the building. How long of a ladder is needed for the job? Now you're going to get some interesting names, as our book loves to use interesting names. I'm not really sure if one of the Osceola Valencia maintenance people is really named Young Sue. I hope this is not like a profiling kind of question, but that's neither here nor there. So off that platform, let's talk about how to draw a picture. And again, my pictures are going to be very, very crude, guys. We're not looking at, I'm not looking for, artists on here. So it says that I have a window of a building. All right, so window. Okay, here's my building. There's my window. Okay. So this window, we know, is 25 feet off the ground. It told us that in the problem. 25 feet. Okay? It says that Yu Sung is put in a ladder 10 feet away. All right? So I'm going to draw in my ladder. Here's my ladder. I know it's awesome. I wish everybody could have a ladder like that. And it's 10 feet away from the building. Okay, so that means I got some little grass down here. Here's my grass. And we know that this length, again, as they just said, we underlined it, it's 10 feet. In the end, they want to know how long is the ladder. All right. So, do you see the right triangle in here? I hope you do, but if you don't, let me highlight it. There's the right triangle. there's that right angle, that perpendicular. So the 25 and the 10, we now know are A and B. They are the legs. How do I know which one is A and which one is B? It doesn't matter. Okay? I could have easily said 25 was B and the 10 was A. It does not matter. That means that the X we're looking for, that's C. All we have to do now is run the problem. A squared plus B squared equal to C squared. Now, I know many of you are thinking, Mr. Armstrong, these are all squared. What is it doing in a section on radicals? You'll see here in a second. So when we fill in, we have 25 squared plus 10 squared equal to C squared. The first thing you're going to take care of is the squaring. So anybody that needs to be squared, we need to do that. So 25 squared is 625. 10 squared is 100 equal to C squared. And if you don't want to put C there, you could also call it X because that's the variable I gave it from the problem. X. Second step, you're going to combine like terms, or in other words, it's going to be addition, but it could be a subtraction step. If we knew what the hypotenuse was and we knew a leg, we'd have to take this value and subtract it over to the other side. Okay, so your second step is either adding or subtracting. It's one or the other. You're not doing both. So all we're going to do in this one is add because it's like terms. So 625 plus 100 is 725 equal to X squared. Your third and final step for solving. This is why it is in this section. Because the third and final step is you're going to square root both sides. Okay? Because how do I get rid of something squared? You square root. Square root. So X is equal to, now normally I would have you give me the exact answer, but because this is a real world problem, if you got the exact answer to this, it would be this. 5 square roots of 29 feet. Okay, that is the real exact answer because we would break down that square root of 725. But again, this is real world. If I went to Home Depot or Lowe's and I come in and be like, hey, I'm looking for a ladder that's 5 square roots of 29 feet. Can you help me out with that? That clerk would either slap me or say, what did you just call me? Okay, because that doesn't make any sense in the real world. So in this problem, they actually want you to round. Now the problem with this is it doesn't actually tell you where to round in the problem. So let me tell you how to deal with this. So we go to our calculator, we put in the square root of 725. The first thing I would start with is I would round to the nearest whole number. So the 9 says, hey 6, go up. So the first answer I would try putting in to iMathAS is 27 feet. Round to the nearest whole first, try that answer. If that answer doesn't work, then go back and round to the nearest tenth. So the 2 says, hey 9, stay the way you are. So I would try 26.9 feet second. If that didn't work, then I would round to the nearest hundredth, 2 decimal places. But I think one of those 2 is going to work. So here is the answer to that first problem. Okay? So here's your problem. Go ahead, pause the video, give it a shot. Okay. So in here, it says that we've got a sign on a building. Okay? Some sort of sign on a building. Blah, 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 blah. There's my building. Kind of looks like a hazmat mask. Weird. All right. And it tells you that the sign is 20 feet off the ground. Okay? So we now know that from here, no, erasing. From here to here, that is 20 feet. And then we call the maintenance person Kong. Again, I don't name these people. So he has a ladder that is 30 feet. All right, cool. Thanks, Kong. Although I'm sure you probably don't need a ladder. So drawing in my pretty little ladder. So we know that this is 30 feet. Okay? We want to know how far from the wall is it. So we got some grass down here. We want to know this distance. That's x. So what all do we have here? Well, in our problem, we have a leg. I'm just going to call it A. You could have called it B. It didn't matter. The 30 is your C. That's your hypotenuse. Because again, in my triangle, if you don't see the triangle, there it is. There's the right angle. These two have to be the legs. So X is B in my case. That's your hypotenuse. So solving the rest of this problem, A squared plus B squared equals C squared. So we've got 20 squared plus X squared, because that's what B is, and C is 30 squared. Okay? So the first step that I had a second ago was do the squaring. So 20 squared is 400 plus X squared. 30 squared is 900. Okay? So the second step says do adding or subtracting, where I can't put these together, so I got to move the 400 over here. So that means I'm going to subtract. So 900 minus 400 tells us that x squared is equal to 500. And our last step says square root both sides. Square root, square root. Again, if we were exact on this, it would be 10 square roots of 5 feet. But if I was with my friend out there trying to put up a ladder and I said, hey, move this back 10 square roots of 5 feet, again, he'd come and kick me and be like, what did you just say to me? And I'd be like, let's take the square root of 500 and be like, oh, I meant to say the 3 says, hey, 2, stay the way you are. Could you move this ladder back 22 feet? That makes more sense in a real world problem. So that's rounded to the nearest whole. If they don't like that number, then round it to the nearest tenth. So the 6 says, hey, 3, go up. So you could also say 22.4 feet. One of these two answers should work. And there you go. All right, last piece. All you're going to do here is evaluate, and you already know how to do this. Remember that these are the x values. Yes, there are 3 equations up there, but you're not plugging into each one. You are plugging into where the variable in front tells you to. And now on this, you do need to make sure that you reduce whenever possible, because they do not want decimal answers on this. So go ahead, pause, and give these a shot. Okay. So when we deal with this first one, it says plug into F, and we're going to put a -1 in for X. So -1 plus 5. Well, what is -1 plus 5? That is 4. And the square root of 4 is 2. There's your first answer. Now we move on to the next one. It really is that easy. We're going to take this -10 and we're going to plug it into G. So right up here, we're going to put a -10. So we've got the cube root of -10 plus 2. Well, -10 plus 2 gives you the cube root of -8. And we know that we can do cube roots of odd powers. So the negative pops out, and that leaves us with the cube root of 8. Well, we actually know what the cube root of 8 is. It's one of our perfect cubes. And the answer is a negative 2. Last but not least, we're going to take the 4 and plug it into the h. So we will have the 4th root of 4 minus 3, which is the 4th root of 1. And just so you know, any radical with a 1 under it is always going to have the answer of 1. So the square root of 1 is 1. The cube root of 1 is 1. The 4th root of 1 is 1. The 5th root of 1 is 1. You get the picture. And that, my friends, is 5.1. Enjoy and have fun.